Hello, good afternoon everyone. I welcome all of you to the most comprehensive exam preparation app, that is BYJU'S app on YouTube channel. So already from past two classes we are studying about strength of material. This is AIMERS batch and we have completed the step bar, temperature stress and SFD BMD for the last class. Today's class is about deflection. So all of you please join fast and do not forget to share and like the session. Let us start with the deflection chapter. Before that, this is my brief small introduction. All of you please do not forget to like the session. There are classes which are to be held in a continuation of this particular AIMERS series. So today I'm considering taking the class for the deflection, and from 22nd October it will be for declination from Ankit sir, then rise and fall on 24th October, then on 26th October it will be photogrammetry by Ankit sir. Then the classes will be for the structure, which will be conducted by Krishna sir for the ILD and truss and displacement method. And after that, once again, this series is not going to be stopped here. It will be continued, and for the soil mechanics and all other subjects will be considered in this particular series. So be there, attend the classes continuously. Obviously you are going to get the benefit from this particular series. Next one, okay, let us find out understanding of slope and deflection. Wait a second. Okay, this slide has slightly, give me 1 second. Oh, that is what I was finding out. Okay, you can also join me on at my Telegram channel, that is Civil by Ansari sir. So whatever the problem, I'll be giving it to here, or maybe if you have some of the doubt, you can always ask me and you can question there on my Telegram channel. These are the staff faculty of the BYJU'S, and they are the star faculty who are taking all the classes for the civil engineering department, and these are the courses which are running for the Vision batch 2022, rank up GATE, and Vision 2023 for those who are aspirants of the GATE 2023. Now let us start with the slope and deflection. Understanding of slope and deflection. There are different methods of finding slope and deflection. So today I'll be teaching you what is the understanding of slope and deflection, then what are the different methods of slope and deflection, then how to approach the problem by using the method of superposition, and I'll teach you today about moment area theorem, right? So today these are the agenda which I'll be covering in the classes. So first of all, deflection and slope. Suppose if you have a beam and the beam is loaded with some concentrated load at the free end, what will happen to this particular beam? It will get bent, of course. If it is going to get bent, what is the meaning of our slope and deflection? If you draw the tangent, if I'm more interested to find out what is the slope at my B point, at B joint, what is the slope? So draw the tangent at B, and whatever the angle you are going to get, that particular angle we are calling it as this angle. This is nothing but your slope at B. What is the deflection? Of course, here whatever the amount by which this point has been deflected, this one we are calling it as deflection. So this is your slope and this is your deflection. At any position on the beam you can find out the slope and deflection. Let us move to the another method. What are the methods to find out that deflection and slope? There is a double integration method and Macaulay's method. Macaulay's method is nothing but same as to double integration method only. Those who have studied, they know that to write down the bending moment equation, Macaulay has identified it has one specific function and bracket by which we are writing down the bending moment equation. Then you have a area moment theorem, you have a conjugate beam method, you have a strain energy method and superposition method. Although you have a virtual work method also, but see, all of them methods, whatever the methods are available for your finding out the deflection and slope, out of all the methods, generally if you'll find it out for the GATE examination or for any of the competitive examinations, mostly helpful methods are nothing but your method of superposition. More than 80% time you will find out that method of superposition, moment area theorem, conjugate beam method and strain energy method. One should, if you are really thinking that in particular deflection chapter you want a very nice holding, then I will suggest that at least you should cover this 4 methodology. At least one should cover these 4 methodology if you are really feeling that you will be able to solve most of the type of problem in your deflection chapter. So once again, I welcome all of you, and please, those who are watching the session, I will request do not forget to share and like. Now coming to the method of superposition. In that particular method, few of the relations, standard relations are necessary. If you are really going towards the method of superposition, one should understand that slope and deflection of some of the standard loading are necessary for you to remember. Then understanding of deflected shape of the beam is also very important. Only if you can remember the formula is not going to help you a lot. So you need to practice a problem in such a way that the deflected shape of the beam also one should understand due to the loading. Then only you can implement your formula whatever you have remembered. Okay, now come to the problem, right? Come directly to the problem. Suppose there are some standard condition I will be providing it to you. Some standard condition I will be providing it to you. This is suppose a concentrated load acting on your cantilever beam. What is the slope for that one? PL square by 2EI, deflection PLQ by 3EI. And if the moment is acting on your cantilever beam, it is ML by EI slope, and the deflection is ML square by 2. Although all these formula you can calculate either by using your moment area theorem or by using your strain energy method or by using your conjugate beam method. But if you are going to use the superposition method, then all the standard relation at least you need to remember it out, right? These are few of the standard relation or slope and deflection I have given for standard loading. Suppose for a simply supported beam, what is the slope and deflection if a concentrated load is acting at mid of the beam? If moment is acting at the one of the support, what is your slope and what is your deflection? Here two formula actually I have given you if you want to go through it. This is the maximum deflection. This is the maximum deflection. And this is the deflection at mid of the beam. This is the deflection at mid of the beam, right? Then for UDL, what is the slope and deflection for your simply supported beam? Now let us go to the one of the equation. If I'll ask you what is the slope and deflection at your free end B, what is the slope and deflection at your free end B? Suppose this is your end A and this is your end B. Now the load is not acting on your beam at a free end. I gave you already a formula when the load is going to act on your free end in your cantilever beam. The formula already you have seen that the slope will be your, if it is P, that PL square by 2EI, and if it is a deflection due to the load acting, it is nothing but your PLQ by 3EI. How you will be utilizing that particular formula if you have remembered that? So due to the application of the load, what will happen? First of all, the beam is going to get bent. Acha, why I am showing this portion of the beam as a bend? Because if you take any of the section between the A and C, suppose this point I am considering as C, between A and C, this portion has a bending moment. You take any of the section in between and you have a bending moment. As long as you have a bending moment, the portion of the beam you can understand it will be going for the bending. But for the portion of CB, if you take any of the section, you don't have a bending moment. So the portion CB will not bend and it will be straight. It will be remaining straight. Are you able to understand that? Now if I'll ask you what is the deflection or slope, how you will calculate. So whatever the slope you are going to get or whatever the deflection you are going to get, you can calculate. See, if you'll just take the deflection here, if I'll ask you what is the deflection at joint B, so you can always calculate the deflection for the beam. It is now kind of cantilever where the load is acting at the free end. So you can calculate the deflection for this particular end, and by finding out the deflection at this location, just by addition another deflection here, you can say that the total deflection can be calculated. The total deflection will be now delta 1 plus delta 2 here. The total deflection at the free end will be nothing but delta 1 plus delta 2. Acha, whatever the slope you have at this particular location, if you draw the tangent, as long as the slope at A is nothing but 0. But slope at C, you have some value which you can calculate, that is nothing but PA square by 2EI. The slope will be continued from C to B. The slope at C or slope at B will be same. So theta at C will be equal to theta at B. Why? Because the portion of the beam CB is going to be straight. As long as the portion of the beam CB is going to be straight, the slope at C and slope at B will be same. Now, delta 1 you can calculate, which is nothing but PL cube by 3EI, and here the L will be length of the beam, which is A. That's fine. But the delta 2 you can calculate. How you can calculate delta 2? As you can see that this portion was straight and it has been rotated by some amount. What is the rotation? That I told you. Whatever the theta you have here, that is nothing but theta at C. That theta at C. Now, actually the rotation, you know that it is kind of arc. But for small deformation, for small deflection, one can consider the arc length and the vertical one as to be same. So arc length, you know how to calculate the arc length. It is nothing but r theta, isn't it? If the length of the beam is L minus A, I'll say that this deflection I can write it down, that is nothing but L minus A into the theta. Theta here, that is theta C. That will be the delta 2. So delta 2 I can write it down. That will be delta 2 L minus A into whatever the theta C you are having here. Theta C is now PA square by 2EI multiply by L minus A. That's all. This will become the, this is the way you will get the deflection at point B. Are you able to understand that? Now consider the another problem. Suppose you have a UDL which is acting over this beam here instead of the concentrated load. What will happen now? Same problem. It is same kind of problem. The portion where you have a bending moment will get bent, and the portion where you don't have a bending moment will be straight. So from here to here it will get bent, and from here to here it will be remaining straight. Once again you will calculate the same way. The deflection here can be calculated by using a normal formula which you have remembered for the standard one. That is, when a cantilever is loaded with your UDL. Cantilever, when it is loaded with the UDL, the slope at, suppose this is B and this is A, slope at B I have given and delta at B I have given. These two you can remember, simply you can implement it here to find out the delta. Delta at C will be. Now after finding out the delta here, of course similar way this will be your delta 1 and this will be your delta 2, and delta 2 you can find out the way I told you. It is nothing but your r theta. So L minus A into whatever the theta you are going to get at C. That's all. So final deformation, the deflection at final free end B will be nothing but delta 1 plus delta 2. Delta 1, as I gave you in the formula section, that it is WA4 by 8EI. This length of the beam is A till from here to here, A to C. And delta 2 is now r theta, which is nothing but L minus A into the slope here, theta at C. Due to the UDL, theta at C is WAQ by 6EI. Are you able to understand that? If you have any trouble, please let me know. See, method of superposition is quite helpful if you are going for any of the competitive examination. Now consider the another problem by using method of superposition. Suppose you have an overhanging beam, and for the overhanging beam, if I'll ask you what is the deflection at the free end, how you will calculate that deflection? You know that if you're applying the load, the beam is going to get bent, because between the point A and B, I can say that between the point A, support A and B, the beam is going to get bent because you have a bending moment. But for the portion, suppose this is joint C, point C, for the portion of BC, you don't have any bending moment. The bending moment on the section of BC as well as for the section of AD, it is 0. If you don't have a bending moment, the section or the portion of the beam is not going to bend there. It will remain straight. Now, if it will remain straight, you know what is the theta at this location. Due to the concentrated load applied here, already I gave you the theta value. And by using that theta value, you can calculate the, so theta for a concentrated load is nothing but WL square by 16 EI. I think if concentrated load at for the simply supported beam, if you have a concentrated load at mid of the beam, then your theta, either you take theta here or theta here. The theta is nothing but, what is that theta? WL square by 16 EI, isn't it? You know the theta value. After knowing the theta value, how you can calculate the deflection? Once again, if it is going to be straight, now you can consider that it has been rotated from here. As I told you, for the small deflection and slope, one can take the arc length as a normal straight length, isn't it? Arc length is your r theta. If the length of this portion is a, I can simply say that the theta, whatever here you have theta b, this is also your theta b, and the arc length here will become nothing r theta, that is a theta b. That's all. That is nothing but your deflection. So delta will be a of theta b, which is a into WL square by 16 EI. Are you feeling comfortable here? Yes, there is a question here, load integration slope and slope integration deflection. Okay. Now suppose you have another problem. Here I am asking, moments of the same sense are applied to both the ends of a simply supported beam. The ratio of the rotation of the two ends is 2. What is the ratio of the applied moment? Can you do this problem? If the moment of the same sense are applied to both the ends of a simply supported beam, can you do this problem? This is very simple. If you know that if a moment will be applied, what is the slope you are going to get? If you are applying the moment, the slope which you are going to get. If you will apply the moment, suppose he's saying that moment of same sense are applied. Same sense means if I'm applying the clockwise moment, I will be applying the same clockwise moment. Suppose if I'm applying the clockwise moment here, that is M at A, this is suppose A and this is B support. Same clockwise moment I'm applying at B also. Due to the application of the moment A, what will be the slope at A and what will be the slope at B? If I'm applying moment at A, the slope at A will be, theta at A will be, due to the application of moment applied at A, ml by 3ei. So that will be ma of L by 3ei. And the theta b will be due to the application of ma. I'll change the color also. Theta b will be ml by 6ei. Now due to the application of the moment at B, what will be the theta? Acha, one more thing you should understand. If you are applying the moment at A, what kind of deflected shape your beam will be having? Due to the application of the moment at A, the deflected shape of the beam will be like this. So the rotation also, you can consider one rotation. The rotation, maybe it is in clockwise and anti-clockwise. So you can consider one as a plus and another one as a minus one. Did you get that? Now due to the application of the MB, what type of deflected shape of beam you will be getting it here? The deflected shape of the beam will be something like this. And here the rotation is opposite to that. And here also the rotation is opposite to that. So I can write it down, the theta at A due to the application of MB will be MB L by 6ei MB L by 6EI, and I will be writing down that as a minus sign. Then theta at A will be, sorry, theta at B will be ML by 3I, that is nothing but plus of MB L by 3EI. Now what he was asking, the ratio of the rotation of the two end is 2. Ratio of the rotation of the two end is 2. So ratio of the two ends, ratio of the rotation he has given. So theta at A, what is the total rotation there? So MAL by 3EI plus that is minus sign will occur, MBL by 6EI, right, divided by what is here, that is minus of MAL by 6EI and plus of MBL by 3EI. This is what he has said, it is equals to 2. It is equals to 2. Multiply by 6EI to the top and bottom, what you will get? Twice of MAL, and 3I will get cancelled, minus MB, LL also will get cancelled, no? LL also will get cancelled. So take the common of LL. So 2 of MA minus MB divided by, how much will get at the bottom? 2 of MB, or I can write down like this, 2 of MB minus of MA equals to 2. If you solve this one, you are going to get MA by MB is equals to 5 by 4. MA by MB equals to 5 by 4. Did you see that? Yes, of course. Why not? Others. Why not mechanical student cannot see this? If you have any trouble here, please let me know. Are you able to understand that? Okay. Going to the next problem. Suppose this is the problem here. An overhanging beam of uniform EI is loaded as shown in below. The deflection at the free end is. How you will calculate the deflection at free end? As I told you, you should remember the standard loading due to the slope and deflection due to the standard loading. But at the same time, you should practice the question to understand due to the load, how one will approach, what kind of deflected shape you will be getting it. So if you don't know, if you are missing the approach, still if you can remember the formula is not going to help you out. How you will do this problem? So there is a problem. You have a beam. Understand the approach first of all. This is the best part of your solving the problem. So this beam, if you are applying the load, what will happen? This W, if you have a length L, this one, and this length is suppose L by 2, due to the application of the W, imagine the beam AB, if it is fixed, suppose if it is fixed, what will happen? See, those who are very new, they will understand it very easily. If it is fixed, what will happen? Normally the beam BC will bend, isn't it? And the deflection, whatever you are going to get, will be simply PLQ by 3I. That's all. You will keep the value of L by 2, W, whatever you have, that PLQ by 3I. But if it is not fixed, what will happen? It is not fixed, no? It will first of all, due to the W into L by 2, there is a moment which is going to occur. Due to that moment, the AB portion is going to rotate. So I am more interested to see that my joint B, if it is fixed, there is no rotation at the joint B. But as long as it is not fixed, there is a slight rotation which will happen. What kind of rotation will happen? The beam AB will get bent due to the moment W into L by 2. Suppose only the moment I am considering over the joint B, the rotation, due to the rotation of the joint B, what will be the deflection at the point C? Without loading, if I am trying to consider it, just due to the moment when the joint B will get rotated, what is the amount of deflection I will be observing at C? Then after that I will be considering my load over C, and then I will bend my beam. So two type of deflection you will observe here. Only due to the rotation at joint B, and another one is due to the loading, the concentrated load which is going to act on the position C. So two deflections we have now. Is it clear? Delta 1 and delta 2. How one can calculate delta 1 value? The delta 1 can be calculated, as I told you, this is delta 1 is nothing but due to the rotation only. So if you know what is the slope at B, same slope is here theta B, and you can use your r theta to find out the delta 1. The length L by 2 already you know that. This angle is your theta B. So how you will find out theta B? You already know that for a simply supported beam, if a moment will be applied due to the application of the moment at support B, your theta is nothing but ML by 3I. Now M already you know that. What is the M value? This is simply W into L by 2. Isn't it? M value here is nothing but, what is M value here? M is nothing but W into L by 2. So multiply W into L by 2, that is M value. Due to that, you will get the theta. So once you know what is the theta, you can calculate the delta 1, which is nothing but theta L by 2 into theta B. That is R theta. Isn't it? And delta 2 will be simply PL by QA, PLQ by 3I. So here it is W into LQ. LQ is L by 2 whole cube divided by 3I. That's all. Add these two. Add these two. So the deformation or the deflection at C will be summation of delta 1 plus delta 2, whereas delta 1 is nothing but your C, L by 2 into theta B, right? What is your theta B? That is nothing but your ML by 3I. M is what? C, W into L by 2. So M L by 3I multiplied by L by 2. That is theta B into L by 2. Then plus your another one, that is W into L by 2 whole cube divided by 3I. That is your total deflection there. Are you able to understand that? Now consider the another problem. Find the deflection at A. Believe me, if you are able to understand the previous problem the way you have approached, here also you are going to do the same kind of approach. If you have to find out the deflection at A, how you'll find it out? First of all, if it is fixed, what will happen? Due to the concentrated load, your beam is going to get bent. Clear, no? And you will find simply PLQ by 3I. But it is not fixed. It is not fixed. What will happen? This joint B is going to rotate. Joint B is going to rotate. So first of all, find out what is the rotation you are going to obtain at joint B. Who will rotate the joint B? It is nothing but the P into, suppose this length is L, P into L, a moment is going to act over here. That is nothing but PL, and due to that moment P into L, this joint B will rotate. What will be the deflected shape of the beam CB? The deflected shape of the beam, suppose CB, will become like this. The deflected shape of the beam, suppose, is going to be like this. Due to this deflected shape of the beam, now see, joint B has been rotated here. If the joint B has been rotated, consider it only due to the rotation, what kind of or what is the amount of deflection you are going to get at this location. So this deflection is only due to the rotation of the joint B. This delta 1 is nothing but only the deflection due to the rotation due to the joint B. Of course, that once again you will go for the same. For the cantilever, if you have a moment here, what is the slope at this location? So theta at this location is how much? Theta at this location is how much? Theta at that location is ML by EI, isn't it? ML by EI. So whatever M is acting here, ML by EI. What is M we have? That is PL. That is PL only, isn't it? So the slope here is nothing but PL square by EI, isn't it? And use that R theta, whatever the slope you are getting, same slope by same amount, because this is a rigid joint. So same slope you'll be getting it here. Multiply with the length and you'll get the deflection delta 1. So delta 1 will become, certainly delta 1 will become length, that is L into PL square by EI. Agree or not? At the same time, Now after that rotation of the joint B, due to the application of the load, this beam is going to get bent. This beam is going to get bent. Now find the deflection due to bending of the beam, which is nothing but your delta 2. Delta 2 is now PLQ by 3I, that's all, plus PLQ by 3I. This is the total deflection. If you add this PLQ by EI and PLQ by 3I, how much you will get? Find 3EI here and kitna 3 or 4, I think 4 PLQ by 3I. So your answer will be 4 PLQ by 3I. Did you get that? Now coming to the moment area theorem, I'll explain that moment area theorem also. What the first theorem says that change in slope from any point x to b. I'll just explain. If you have a beam, listen me carefully. If you have a beam, if you are applying the load, it will get deflected, of course. I'm showing you too much of deflection just for understanding purpose. As per the first theorem, what it explains that if you are interested to know the angle between the 2 points, draw the tangent at the 2 points. Suppose I'm going to draw the tangent between these 2 points. Wait, I have drawn the tangent between these 2 points at the free end and maybe at some another position x. Suppose this free end is b, this A and this is b. If I'm drawing the tangent between these 2 points, as per the moment area theorem, it says that draw the bending moment diagram, then draw the M by EI diagram. So this bending moment diagram for this concentrated load on a cantilever will be triangle, isn't it? It will be a triangle. Then find out the M by EI diagram. This is nothing but your M by EI, means a bending moment divided by the EI of the beam. Draw the bending moment diagram, then divided by EI of the beam. What you will get here? This bending moment as per this is PL. This is negative, of course, and you will get PL by EI. This is your M by EI diagram. As per the moment area theorem, if you will find the area, between these 2 points on your M by EI diagram, area between these 2 points on your M by EI diagram, this is your M by EI diagram. On your M by EI diagram, if you are finding out the area between these 2 points, it will provide you the angle drawn between these 2 tangents. Angle drawn on the deflected shape, if you are drawing the tangent, this angle you will be getting it out. But fortunately, this is not that much helpful for us. What we will do now? You will get this angle. But what we will do with this angle? Generally, people are asking what is the angle at free end, right? Slope at free end. So we are not much interested in this particular angle right now. So what we are doing, we are simply applying our understanding. And what we are doing, instead of considering the point at x, instead of considering or drawing the tangent at x, we are going to draw the tangent at A. If I am going to draw the tangent at A, what will happen? Of course, as per the conversation, what I told you, if you are interested to know what is the deflection, see, if you are drawing the tangent, 2 tangents here, these are the 2 tangents, no? So you will be getting this angle. Of course, this angle is useful for us because this angle tells me that directly it is nothing but the slope at free end B, isn't it? This is nothing but the slope at free end B. I am interested to know this particular slope. So instead of considering the tangent at x, I have taken the tangent at A, because tangent at A, the slope at A will be 0. You already know that it is a fixed one and theta at A will be 0. Now, as per the moment area first theorem, if I'll take the area, of M by EI diagram, it will provide me the slope between the 2 tangent. But ultimately, as you know, the slope at A is 0. The slope between the 2 tangent actually will become nothing but the slope at B. That is how several times you have heard that moment area theorem is good for the cantilever beam, because in a cantilever beam you are 100% certain that at a fixed support the slope will be 0. So you are always considering the 2 position at free end at the fixed end, because at the fixed end you have a slope every time 0. So now you take the area of the M by I diagram and it will give you the slope between the tangent A and B, but fortunately slope at A is 0, so of course you are going to get the slope at B only. right? So theta at B, you will get it. That is nothing but area of M by I diagram. Area of M by diagram, half into base into height. That's all. Half into base into height. And if you calculate, it will become PL square by 2EI. That's all. This is your M by EI diagram. What second theorem says that? For the moment area theorem, if you are interested to know how to find out the deflection, what second theorem says that? Listen to it very carefully. Yes, Suraj. From this moment area theorem, you can do that. But moment area theorem is not applicable to the beam which has hinge, and at the same time, it is more comfortable for using a cantilever beam, or maybe if the simply supported beam have a symmetrical load. See, first thing you have identified, no, here every time we are going to use that theta at A even after the deflection will be 0. For the simply supported beam, in a symmetrical loading only, we are sure that the theta or the slope at the mid of the beam will be 0. If you have a different asymmetric type of loading, one cannot identify, or it will be now become a lengthy procedure to find it out where the slope is 0, isn't it? So more easily you can apply the moment area theorem if you have a cantilever beam or the simply supported beam with the symmetrical loading. Now how to find out the deflection? First of all, same problem, just you consider it here. Same problem, you consider it here. Of course, if you are applying the load, you will get, your beam will get curved. Then draw the tangent at these 2 points the way you have drawn it earlier. Then draw the M by I diagram. Draw the M by I diagram. What is your M by I diagram? That is PL by EI here. After drawing the M by I diagram, it says that if you will calculate the, see, earlier you have taken, see, this was your X point and this was suppose your point B, isn't it? Earlier you have said that the area between these 2 points will provide you the slope. Now he is saying that the moment of this area, what's that? Listen carefully. The moment of this area will give you the deflection. Moment of area will give you the deflection. Then another question you may ask, sir, where I should stand? Maybe on the line which is drawn from the X, or should I stand at the line at B? Understand that. Which deflection you will actually identify? If you are taking the moment, by standing at B, of course you are calculating this deflection. Means the vertical intercept is also necessary here. Now, if you are calculating the moment by standing at this position, you are getting this deflection. The difference between the tangent which has been drawn at X and at B. This deflection you will be getting. But is it necessary for us, or what we will do with this one? Sometimes we can utilize it, but this is the understanding of your moment area theorem. This deflection you will get it. Once again, we will now change it. Once again, because we are more interested to know the deflection, the final deflection at B, isn't it? So what we'll do? We will, instead of drawing the tangent at X, we will be drawing the tangent at A. We'll be drawing a tangent at A, because after deflection also there is a no deflection at A. So slope was 0 at A, and the deflection also is 0 at A after deflection of the beam. So after drawing the tangent here, you can identify what I told you. If you have taken the vertical intercept at B, if you are standing at B, what is the vertical height you are getting it? By taking the moment of the area. If you have considered the point A, now between the A and B, this is the total area. If you take the moment of this area by standing at B, you will get which vertical height you will be getting. Which vertical height? This difference between the two tangent. The vertical distance between the two tangent. This height you will be getting. Are you able to see that? Now, of course, this is helpful for us because it will provide me directly, because no deflection at A. So finally I will be getting the deflection at B itself. Right? So I'm standing at B, taking the moment. So there must be some centroid position of this area. that is 2 by third of L from here, 2 by third of L of L, just to calculate the moment of this area, and you will get the deflection at B. Moment of area M by EI diagram. What is the moment of area? That is half into base into height is totally nothing but area. Half into base into height is nothing but area, multiply with the length, that is 2 by third of L, and you'll get the deflection at B. Did you get that? And it will become now PL cube by 3I. Are you able to understand that? Now solve some problem here. A simple beam of span L carries two equal unlike couples M at two ends. The central deflection of the beam EI is given constant. The central deflection of the beam he's asking. Two equal and unlike couples are acting on a simply supported beam. If you have a simply supported beam and two equal and unlike couples are acting over here, equal and unlike, understand that, means you have suppose M here and M here, unlike with respect to the orientation. If one is acting clockwise, another one is acting anti-clockwise. Equal in the sense of magnitude. So equal and unlike couples are acting over simply supported beam. Now he's asking what will be the central deflection here. What will be the central deflection? If you want to use the moment area theorem, what you will do? First of all, you will draw the M by EI diagram, isn't it? What is the bending moment diagram for this one? What will be the bending moment diagram for this one? The bending moment diagram for this one will be, of course, it is a sagging of beam, and you will get this is the bending moment diagram. If you are dividing by EI, throughout your EI for the beam is constant, so this will become now M by EI and M by EI. This is your M by EI diagram of your beam applied with the moment both ends. What is your deflected shape? I'll just consider another color. Due to the application of the moment, the deflected shape of the beam will be like this. And it is symmetrically loaded. You can understand that you have a slope at the mid of the beam will be 0. Slope at the mid of the beam will be 0, isn't it? So just consider that this is your mid of the beam. I am more interested to find out the deflection, the central deflection. As per the moment area theorem, now you try to understand and implement it here. Implement the moment area theorem here. Draw the tangent at A. Draw the tangent at A. Suppose this is the tangent at A. And draw the tangent at the mid of the beam. Delete this all. Draw the tangent at mid of the beam. As you know that slope at mid of the beam is 0 if you are drawing the tangent, now you tell me, as per moment area theorem, if you want to apply to find out the deflection, the central deflection, what moment area theorem says that the area, first of all, between the M by A diagram, take the moment of the area between the two tangent points you have drawn. So two tangent point you have considered. Of course, while considering the two tangent point, you will be having a two vertical intercept also. Isn't it? There are two intercepts I have drawn here. At one vertical intercept I have taken at A, and another vertical intercept maybe I have taken at C. You already know that between these two, whatever the M by EI diagram you have, if you are going to take the moment of this area, you will get the deflection. But one should be very clear about which side you are going to stand. Now, as I told you, if you are drawing the tangent between A and C, if you are drawing the tangent between A and C, if you are standing at C intercept, if you are standing at C intercept and taking the moment of this area, you will get this vertical height, the distance vertical height between the two tangents, the vertical height between the two tangents. Tell me, is it now useful for us? Is it now useful for us? Not at all. So you should be very clear about that, what you are going to do here. Instead of that, if you are going to stand at this position to take the moment, you'll get the vertical height between the two tangent. You will be getting this height by considering the moment of the area. Yes, this is actually what we need, because this is nothing but your central deflection here. So at which intercept you are going to stand? You are going to stand at intercept A to find the central deflection. So moment must be calculated by standing at A position. Are you able to understand that? Not at C position. Not at C position. Is it clear to all of you? This is very important. Moment will be found out. Moment must be calculated. Moment of this area must be calculated by standing at intercept of A. The vertical intercept by drawn at A, you are going to stand. If you have any doubt, please ask me. And do not forget to like the session. So just calculate the moment of this area. What is the total area here? The total area is nothing but your total is rectangular. So M by EI multiplied by L by 2 multiplied by, if you are standing here, simply multiplied by L by 4. That's all. That will give you the central deflection. So it will become now ML square by 80. That's all. Is it clear? Is it clear? Now solve another problem here. Find the slope at free end for the beam as shown in figure. For the cantilever, if the cross-sectional area is getting changed, or EI, some EI value, somewhere if the EI value is going to get changed, you can simply apply your moment area theorem. How you can find the slope at the free end for the beam as shown in figure? First of all, you will be drawing the M by EI diagram, isn't it? First of all, you will be drawing the M by EI diagram. Let me draw the bending moment diagram for this one first. What will be the bending moment diagram? At all the section, at whatever the section you are standing, it is only M. So of course the bending moment diagram will be hogging, it is -1, but it is M. So the bending moment diagram throughout is nothing but your M. Agree or not? This is your bending moment diagram. Now EI is getting changed from here. If you divide by EI, so from A to C it is 2I, and from C to B it is I. So if you will divide by EI, what will be your M by EI diagram? So M by EI diagram, if you will consider, suppose if this is divided, this will be divided by EI. So here you have a EI. And if this side you are going to divide, it will be divided by 2EI. So it will be M by 2EI. Are you able to understand that? It will be M by 2EI and it will be M by EI only. This will be your M by EI diagram. Isn't it? This will be your M by EI diagram. He's asking find the slope at the free end. To find out the slope at the free end, what you'll do? It is nothing but the area. It is nothing but the area. So if you are interested to know what is the slope at free end, of course you are going to consider the tangent at A and tangent at B. Slope at A will be 0 because it is a fixed one. So the area, just if you will calculate the area of M by EI diagram, will provide you the slope at the free end B. That's all. What will be the area? What will be the area? See, two rectangle you have. Length here is L by 2 and here also L by 2. Simply you take the area of that. M by 2 EI multiplied by L by 2 plus M by EI multiplied by L by 2 multiplied by L by 2. Just to calculate how much you get, ML by 4 EI and plus ML by 2 EI. If you add these two, you'll get 4 EI here and 4 ka 4 2 2 na 4 2 3 ml. 3 ml by 4 EI. That's all. Are you able to understand that? I hope it was useful for you. Now you know that this series will be continued, the AIMERS series. All the subjects will be covered here by different faculty. Just you be there along with us and get the benefit of all this subjects and the concept of the subjects. Thank you everyone. Thank you everyone. We'll meet once again.